There is something about light that almost nobody ever stops to think about. And I mean really think about. Not the speed, not the colors, not even the waves. Something far more fundamental than any of that. Something that, the moment you try to answer it seriously, pulls you into the strangest and most beautiful story in all of physics. Welcome to Feynman's Path. Today, we're going to pull on that thread all the way. Now, before we go anywhere, let me be clear about what we're not talking about. This isn't a video about how light is fast. Yes, it travels at roughly 186,000 miles per second in a vacuum. We've all heard that. It's not a video about sunscreen or why the sky is blue, though those are genuinely wonderful questions for another day. What I want to talk about today is something that sounds almost embarrassingly simple. When light moves from one place to another, what exactly is doing the moving? That's the question. Hold it in your mind for a second. What is moving when light moves? Because here's the thing, if you try to answer that honestly, if you really sit down and follow the logic wherever it leads, you end up somewhere extraordinary. You end up with a picture of reality that is nothing like the one you walk around with every day. And by the time we're done today, I think you'll find that even the most ordinary thing flipping on a lamp in your bedroom, looking out a window on a sunny afternoon, will never feel quite the same. Let's start with the picture. The picture that all of us carry around without even realizing it. You're sitting in a coffee shop. Morning light is streaming through the window. You watch the dust particles floating in that beam of light. The sun, nearly 93 million miles away, is sending something across the void of space. That something travels in a straight line. It crosses your window, lights up the dust, hits the far wall, bounces, and your eyes pick it up. You see the room. Now, intuitively, what is that something? If you press most people, they'll say one of two things. Either it's like little bullets, tiny particles shooting through space, like microscopic BBs fired from the sun. Or they'll say no, it's a wave, like ripples on a pond. The sun disturbs something, and that disturbance rolls outward, and eventually it reaches us. Both of these pictures feel completely reasonable, don't they? Both of them feel like they could be right. In fact, for a long time, some of the smartest people in history fought viciously about which one was correct. Isaac Newton was firmly in the particle camp. He had good reasons. Christian Huygens championed the wave picture. He had good reasons too. But here's the problem. Both pictures have a fatal flaw hiding inside them. And those flaws aren't just minor technical quibbles. They cut right to the heart of what light actually is. And the strangest part? Following those flaws, really chasing them down, is what led humanity to the two greatest revolutions in physics of the 20th century. Let's take the wave picture first, because this is where things get immediately strange. If you've ever watched ripples spread across a still pond, you know what a wave looks like. You throw a pebble in, and the disturbance spreads outward in circles, smoothly, evenly. Now here's the question, what is doing the waving? The water, obviously. The water molecules move up and down, passing the disturbance along to their neighbors, and the pattern propagates across the surface. But notice something crucial. The water itself doesn't travel from one end of the pond to the other. If you put a little cork on the surface, it bobs up and down as the ripples pass, but it doesn't drift across the pond. The water stays roughly in place. What moves is the pattern of the disturbance. Same thing with sound. Sound is a pressure wave moving through air. The air molecules don't all flow from your mouth to someone's ear across the room. They wiggle back and forth, compressing and expanding, handing the disturbance along to neighboring molecules. The pattern moves, the medium stays. Every wave we know in everyday life needs a medium, some physical stuff to do the waving. Ocean waves need water. Sound waves need air. Seismic waves need rock. So if light is a wave, what is it waving through? In the 1800s, this was not a strange question. It was a completely logical one. Physicists reasoned, if light is a wave, it must need a medium. And since it travels through the void of space, through places where there is no air, no water, no anything, we know that medium must be something else entirely, something invisible. Something that fills all of space, even the emptiest regions of the cosmos. They called it the luminiferous ether, the light-carrying ether. And this wasn't fringe thinking. This wasn't the belief of crackpots or mystics. This was the consensus of mainstream physics for most of the 19th century. The ether was considered as real as the air in this room. It had to exist. There was no other logical option. You can't have waves without something to wave through. So naturally, scientists set out to detect it, and this is where it gets good. Think about it this way. If the ether is filling all of space, and the Earth is moving through space in its orbit around the Sun, then relative to the ether, the Earth is constantly plowing forward, like a boat moving through water. And if that's true, then light traveling in the direction of the Earth's motion should be slightly slower, like swimming against the current, and light traveling perpendicular to the motion should be slightly faster. Even a tiny difference would be measurable with the right equipment. In 1887, two physicists in Cleveland, Ohio, Albert Michelson and Edward Morley, built exactly that equipment. They designed an extraordinarily sensitive apparatus that would split a beam of light, send the two halves off in perpendicular directions, bounce them back with mirrors, and then recombine them. If the ether was real and the Earth was moving through it, the two beams would take slightly different amounts of time to return, and when they recombined, they'd be slightly out of step. The experiment was elegant. The reasoning was airtight. They ran the experiment. They waited. They measured. Nothing. Not a whisper of a difference. Zero. It didn't matter which direction they pointed the apparatus. It didn't matter what time of day, what season of the year. The speed of light was the same in every direction. To any measurable degree, which in this case was extraordinarily precise, the ether simply didn't exist. This result was so unexpected, so deeply uncomfortable, that many physicists initially refused to accept it. The Michelson-Morley experiment is sometimes called the most famous failed experiment in history. Not because it was done poorly, it was done brilliantly, but because it failed to find what everyone was absolutely certain was there. The ether was gone. And with it, the comfortable picture of light as a wave in some physical medium. So what was left? If light is a wave, but there's nothing for it to wave through, what on earth is it? This is where a Scottish physicist named James Clerk Maxwell enters the story. And his contribution is, I think, one of the most beautiful things in all of science. Maxwell, working several decades before Michelson and Morley, had written down 4 equations describing electricity and magnetism. Just 4 equations. They looked simple enough on the surface. But Maxwell noticed something extraordinary hiding inside them. When you combine these equations in the right way, you can derive that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Back and forth, and these two fields can sustain each other, leapfrogging through empty space in an endless cycle. Now, how fast would this self-sustaining leapfrog travel? Maxwell calculated it, and the number he got from pure mathematics, from equations about electricity and magnetism that had never directly referenced light at all, was approximately 186,000 miles per second, which was, within the measurement error of his time, the known speed of light. Maxwell wrote, in what must have been a moment of almost uncontrollable excitement, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Light is an electromagnetic wave, not a vibration in some mysterious mechanical medium, not the ether, an oscillating pattern of electric and magnetic fields mutually sustaining each other, carrying themselves through empty space." Let me give you a picture for this, because it's genuinely hard to imagine. Think about a long line of dominoes. Each domino, when it falls, knocks over the next one. Now imagine that instead of dominoes, you have a chain of invisible flags in space, each flag representing a point in the electric field. When one flag flutters upward, it triggers the magnetic flag next to it to flutter in a perpendicular direction, which triggers the electric flag beyond that to flutter, and so on, endlessly, at 300 million meters per second. Nothing physical is traveling. No substance is flying through space. What's moving is the pattern, the information encoded in the changing values of the fields. This is extraordinary. Think about what it actually means. When the light from this screen reaches your eyes, no matter is moving from the screen to your pupils. No particles are flying across the room. What's traveling is a pattern of disturbance in the electromagnetic field, a field that exists everywhere, even in the total vacuum of deep space, because the field itself is a fundamental property of the fabric of reality. And this is why there's no need for an ether. The medium for the electromagnetic wave is the electromagnetic field itself. The wave doesn't need something to wave through, because the wave is the field changing. You don't need a river to have the river flow. This is the first deep insight. Take a moment with it. The light reaching your eyes right now isn't a stream of tiny bullets sailing through air. It isn't ripples in some invisible cosmic fluid. It is a self-propagating pattern of oscillating electric and magnetic fields, carrying itself through reality at the maximum speed the universe permits. That's already remarkable. But we haven't gotten to the truly strange part yet. Not even close. Here's a question that seems simple but absolutely isn't. Why does light always travel at the same speed? Not just in the same medium everywhere, for everyone, no matter how fast they're moving. Let me set up why this is so deeply weird. You're on a train platform, and a train is passing you at 100 miles per hour. Someone on the train throws a ball forward at 30 miles per hour. How fast does the ball look to you, standing on the platform? 130 miles per hour. You add the speeds. That's just how speeds work. It's so obvious we barely think about it. Galileo formalized this intuition 400 years ago, and nobody questioned it for centuries. Now, someone on that train turns on a flashlight and points it forward. The light shoots out the front of the flashlight at 186,000 miles per second. How fast does that light look to you, standing on the platform? Your instinct says 186,000 miles per second, plus the speed of the train, just like the ball, add the speeds. But no, that's not what happens. You measure the light. It's traveling at 186,000 miles per second exactly, not a hair faster. The person on the train measures it too, also 186,000 miles per second. The speed of light is identical for both of you, even though you're moving relative to each other. This isn't a trick. This isn't a matter of measurement error. This has been tested thousands of times, in dozens of ways, with extraordinary precision. The Michelson-Morley experiment was one of the first pieces of evidence. Decades of subsequent experiments confirmed it beyond any possible doubt. The speed of light is constant for every observer in the universe. No matter how fast you're moving, no matter in what direction, light always arrives at exactly the same speed. Now, I want you to feel the weight of that for a moment, because it breaks something. If speeds always add up the way we expect, if that's a fundamental rule of reality, then light can't be the same speed for everyone. It's a mathematical impossibility. Either light obeys the speed-adding rule like everything else, or it doesn't. And the experiments say it doesn't. So, one of our deepest assumptions about the universe is wrong. Which one? This is exactly what a young patent clerk named Albert Einstein sat with in 1905. And he did something that, in retrospect, seems both obvious and completely audacious. He didn't try to explain why light was special. He didn't try to patch up the speed-adding rule. He said, what if the light speed is the fundamental truth and everything else has to be rebuilt around it? What if the speed of light is the bedrock and it's space and time that are flexible? The special theory of relativity is the result of following that thought wherever it leads. And where it leads is somewhere that sounds like science fiction but is one of the most precisely confirmed theories in the history of physics. If the speed of light is constant for everyone, if the universe insists on this absolutely, then to make the math work, space and time cannot be fixed. They must stretch and compress depending on how fast you're moving. The faster you move through space, the slower time passes for you. The faster you move, the shorter distances appear in the direction of your motion. Time and space are not two separate, rigid things. They're two faces of a single, flexible fabric spacetime, and they bend to preserve the constancy of light. Does this actually happen? Yes, we measure it constantly. GPS satellites orbit the Earth at roughly 8,700 miles per hour. At that speed, the clocks on those satellites tick slightly slower than clocks on the ground by just under 7 microseconds per day due to velocity. That's a tiny difference in isolation. But if you ran the GPS system without correcting for it within a single day, your navigation would be off by more than a mile. Every GPS device you've ever used, in your phone, in your car, in an airplane, carries a relativistic time correction. Special relativity isn't a philosophical abstraction. It's built into the technology you use every day. And here's something even wilder. High in the upper atmosphere, cosmic rays, high-energy particles from deep space slam into air molecules and create short-lived particles called muons. A muon, by rights, should decay almost instantly. Moving at normal speeds, it wouldn't survive long enough to travel more than a few hundred meters. It certainly shouldn't reach the Earth's surface, thousands of meters below. But they do. We detect them down here all the time. Why? Because they're moving so fast, close to the speed of light, that time, from our perspective, runs extremely slowly for them. Their short lifetime, which seems like a brief flicker to us, is plenty of time from the muon's own perspective. They age slowly and arrive. The universe isn't bending its rules. The universe is enforcing its one absolute rule, the constancy of light, and squeezing everything else to fit. Now, I want to take you one step further. And I need to warn you, this is where your intuitions will begin to fail. But don't worry, that's the point. What does the universe look like from the perspective of the light itself? As you move faster and faster, time dilates, it slows down for you. Follow this to its logical conclusion. What happens when you reach the speed of light? Time stops. Completely. A photon, a particle of light, experiences no passage of time whatsoever. When a photon leaves the surface of the sun and travels 93 million miles to reach your eye, that journey takes about 8 minutes from your perspective. But for the photon, 0. Not 8 minutes compressed into a shorter felt duration, literally 0 duration. The photon is emitted and absorbed in the same instant. There is no journey, there is no during, there is only the emission and the absorption, simultaneous. The photon that started at the Big Bang and has been traveling for 13.8 billion years to reach a telescope on Earth, that photon has aged not 1 instant. I need to pause and be honest with you here, the way a good physicist should be. When I say, from the photon's perspective, I'm skating on thin ice mathematically. A photon has 0 mass, and the equations of relativity break down when you try to define a reference frame for something moving at exactly the speed of light. The math doesn't allow it. What I'm describing is an extrapolation to the limit, a conceptual approach that the equations hint at but don't fully authorize. Richard Feynman was obsessive about this distinction. The equations tell us something precise. The stories we tell about the equations are approximations. They're useful, they aid intuition, but they are not the thing itself. The map is not the territory, and in physics, at the edge of what we know, the map can actively mislead you if you forget it's just a map. I tell you this not to hedge or to undermine what we've been building, but because intellectual honesty is not a weakness. It's the whole point of the exercise. And Feynman would have had no patience for someone who pretended otherwise. So, we have this extraordinary picture. Light is a self-propagating electromagnetic pattern. It travels at the same speed for every observer. To protect that constancy, the universe warps time and space. And from the photon's own frame, to whatever extent that's even a meaningful thing to say, no time passes at all. The source and the destination are the same moment. And now we arrive at the question that generates the real philosophical earthquake. Is light a wave or a particle? You've probably heard that the answer is both. But that answer, as usually stated, is almost completely useless. It just restates the confusion without illuminating anything. What does it actually mean? Let me show you why this question cuts so deep. First, the particle side of the story. In 1905, the same year, Einstein published Special Relativity. He also published a paper about something called the photoelectric effect. This is the paper that actually won him the Nobel Prize, not relativity. The photoelectric effect is this. Shine light on a metal surface and electrons fly off. Seems simple enough. Light brings energy. Electrons absorb the energy and escape. Fine. But here's the strange part. The energy of the electrons that fly off doesn't depend on how bright the light is. You can blast the metal with light so intense it would blind you, and if you use the wrong color of light, no electrons come off at all. But use the right color of light, even extremely dim light, barely a glimmer, and electrons pop off immediately. The energy of the escaping electrons depends only on the color of the light, on its frequency, not on its intensity. This makes no sense if light is a continuous wave. A brighter wave carries more energy. A more energetic wave should hit the electrons harder and kick them off with more energy. That's how ocean waves work. Bigger waves carry more energy and hit the shore harder. Einstein's explanation was radical. Light is not a continuous wave. It comes in discrete packets, tiny bundles of energy. Each bundle carries an amount of energy determined by its frequency, its color. A higher frequency bundle carries more energy per bundle. A lower frequency bundle carries less. Brightness just means more bundles per second, not bigger bundles. An electron can only be kicked free if a single bundle hits it with enough energy to overcome its binding to the metal. It's like pushing a heavy boulder off a cliff. You need one good hard shove. Lots of weak pushes don't add up, they just make the boulder tremble. You need the right bundle, carrying the right energy. Too weak a bundle and the electron just absorbs it and vibrates a little. Strong enough bundle and pop. These bundles are what we now call photons. So light comes in discrete quanta, individual particles if you like. You can fire photons one at a time, put a sensitive enough detector in a dark room, and you can hear individual photons arriving, click, click, click. Not a smooth flow, discrete events, like individual raindrops, not a continuous stream. Now here's where the floor drops out from under you. Take a screen with two narrow slits cut into it. Fire photons at it. On the far side, you have a detector screen. If photons are particles, you'd expect something simple. Each photon goes through one slit or the other and makes a mark on the detector screen. Fire millions of photons, and you'd get two bright bands, one behind each slit, straightforward. What actually happens? You get an interference pattern, alternating bright and dark bands, many more than two, spreading out across the detector screen in a characteristic wave pattern. Dark bands where photons almost never land, bright bands where they cluster. This is the signature of waves interfering with each other. When two wave crests meet, they reinforce and you get brightness. When a crest meets a trough, they cancel and you get darkness. But photons are particles. Particles don't interfere with each other the way waves do. Okay, maybe the interference is happening between different photons, some weird interaction when many are traveling at once. Let's test that. Fire the photons one at a time. One photon. It hits the screen. You record where it lands. Then another. Then another. One at a time. No two photons in the system simultaneously. Wait long enough. The interference pattern reappears. Each individual photon lands at a location that follows the probability distribution of the interference pattern. Over thousands and thousands of individual photon hits, the pattern builds up. Bright bands where photons tend to cluster. Dark bands where they almost never go. A single photon. Two slits. An interference pattern. The only way this is possible is if the photons somehow pass through both slits simultaneously. It was in two places at once. It interfered with itself. Let that land. Now maybe you're thinking, all right, fine, I can't see the photon in transit, so maybe it is going through both slits somehow. But what if I just watch? What if I set up a detector at one of the slits to find out which one the photon went through? You do it. You install a detector. Now you know which slit each photon passes through. The interference pattern vanishes. When you observe which slit the photon used, you get two bands, one behind each slit. Normal particle behavior. The moment you stop observing, the interference pattern comes back. The moment you watch, the strangeness collapses. This is not a metaphor. This is not a philosophical puzzler. This is an experimental result, reproduced thousands of times, with exquisite precision, in laboratories all over the world. Feynman described this experiment as containing the entire mystery of quantum mechanics. He said, and I'm paraphrasing here, in the spirit of how he always talked, nobody really understands this experiment. Not in the sense of having an intuitive picture that clicks into place. You can learn to calculate what will happen. You can learn the mathematics that describes it perfectly. But if you try to form a picture of what is really happening at the quantum level, you will tie yourself in knots. The experiment defies every classical picture. And the right response, Feynman always insisted, is not to force it into a picture you're comfortable with. The right response is to sit with the discomfort, master the mathematics, and be honest about the limits of our intuition. He used to tell his students, do not keep asking yourself, but how can it be like that? Because you'll go down a blind alley from which nobody has yet escaped. So what is the photon actually doing? Is it going through both slits? Is it going through one slit while somehow knowing about the other? Is there some hidden variable we're missing, some property that determines which slit it uses, that we just haven't found yet? Physicists have been arguing about this for 100 years. There are at least a dozen different interpretations of quantum mechanics, each internally consistent, each making the same experimental predictions, each with brilliant physicists defending it. Copenhagen interpretation, many worlds, pilot wave, relational quantum mechanics, cubism. They all give you the same right answers to every test. And nobody knows which story, if any of them, describes what's actually real. This is not a failure. This is science working as intended. The mathematical machinery predicts correctly. The interpretational question, what is really happening, may be a question that our human intuitions are simply not equipped to answer. Because our intuitions evolved to navigate a world of medium-sized objects moving at low speeds, not to grasp the reality of fields and quanta and the structure of space-time. Now, I want to show you something that brings everything we've discussed together into a single, beautiful, slightly vertiginous unity. It comes from Feynman himself, his own framework for understanding how light behaves. He called it the path integral approach. Here's the conventional picture of how light travels from point A to point B. It takes the straight line path, the shortest route, the fastest route. We learn this in school as the law of rectilinear propagation. Light travels in straight lines. But Feynman showed something astonishing. The real story is completely different. A photon traveling from A to B doesn't just take the straight line path. Mathematically, and Feynman showed that the mathematics here isn't fiction, it's reality. The photon takes every possible path simultaneously, every conceivable trajectory, the straight line, wild zigzag paths that veer completely off course, paths that loop around behind you, paths that absurdly shoot off to the Andromeda galaxy and come back, all of them, all at once. Each path contributes a little arrow, a probability amplitude pointing in a direction determined by how long that path takes. Now, here's the key. When you add up all these arrows, the ones for the crazy looping paths point in all different directions and mostly cancel each other out. They're incoherent, like a room full of people shouting random words. The noise averages to nothing. But the paths near the straight line, the minimal time paths, their arrows all point in roughly the same direction. They reinforce each other. They survive the sum. And so, overwhelmingly, the photon arrives as if it took the straight line path, not because that's the only path, but because all the other paths cancelled themselves out. The law of rectilinear propagation. Light travels in straight lines is not a fundamental rule of the universe. It is an emergent pattern arising from the quantum cancellation of all other possibilities. The law of reflection angle of incidence equals angle of reflection when light bounces off a mirror, same thing, not a fundamental rule. An emergent consequence of the sum over all possible angles, where only the paths near the minimum time survive. Snell's law of refraction, how light bends when entering water or glass, same thing. Feynman derived all of classical optics from this single principle: add up every possible path. The familiar laws of light are averages, shadows of a deeper quantum reality. Feynman loved this. He spent years simplifying and unifying physics, looking for the most economical foundation. And what he found was this: you don't need to memorize a dozen separate optical laws. You need one principle: sum over all paths. Everything else follows. This was his genius, not just to be clever with mathematics, but to find the level of reality where the complexity dissolves into simplicity, where the many rules turn out to be consequences of one truth. And now I want to take a step back and look at what we've built here today, because I think there's something important in how this picture as a whole feels. We started with what seemed like a naive question. What is moving when light moves? We thought we knew the answer. Particles or waves, one or the other. Clean, intuitive, manageable. What we found instead was this: light is an electromagnetic disturbance, a self-sustaining oscillation of fields that requires no medium because the fields themselves are the medium. Something is moving, but that something is not matter. It is the pattern of change in fundamental properties of space. The speed at which that pattern travels is the deepest constant in the universe, not just a fast number, but a structural feature of reality, the speed limit of causality itself, the rate at which influence can propagate. And to protect that constant, the universe is willing to warp time and space. Time is not a fixed background. Space is not a fixed stage. They are flexible, observer-dependent aspects of a four-dimensional fabric that bends around the speed of light. When we try to understand the nature of the photon particle or wave, we discover that the very concepts we're using are too crude to grasp the reality. The photon is neither a classical particle nor a classical wave. It is something more fundamental than either, something that presents a particle face when we measure position and a wave face when we measure propagation, but is in its own nature something that our language and intuitions don't have a word for. And at the deepest level, via Feynman's path integrals, even the photon's journey dissolves. There is no single path. There is a sum over all paths, a democratic cacophony of possibilities, most of which cancel, leaving only the ghost of the classical trajectory as a statistical residue. What does this mean for us? What does it mean for how we move through the world? I've thought about this a great deal. And I want to be careful here, because there's a temptation when you learn that reality is strange at the quantum level to leap to mystical conclusions. To say things like, everything is connected, or consciousness creates reality in some vague, untethered way. That's not what I'm doing. The strangeness of quantum mechanics lives at the scale of photons and electrons, and quantum effects don't straightforwardly scale up to the level of human experience in the way that kind of talk implies. But I do think there's something genuine to take away. something that Feynman himself embodied. The universe is stranger than we have any right to expect. Our intuitions, built by evolution for navigating a world of rocks and rivers and other people, are not a reliable guide to ultimate reality. The tools we need are mathematics, careful experiment, and above all, the intellectual courage to follow the evidence wherever it leads, even when it leads somewhere that makes us uncomfortable. Feynman used to say that science is a way of not fooling yourself. It's a method for checking your own wishful thinking against what the universe actually does. And the universe, he found again and again, is far more interesting than any story we would have invented for it. Think about what light has taught us. We thought we understood it, particles or waves, one or the other, simple enough, and the refusal of light to fit our categories gave us special relativity, which revolutionized our understanding of space, time, and energy. Light's stubbornness about its own speed led Einstein to conclude that time itself must bend. Then the photoelectric effect told us that light comes in discrete packets, which opened the door to quantum mechanics, which is the foundation of chemistry, materials, science, and essentially all of modern technology. The transistor in your phone, the laser in your DVD player, the MRI machine in a hospital, all of this is quantum mechanics made practical. All of it traces back to the puzzle of what light is. The strange behavior of photons in the double-slit experiment told us that reality, at its foundation, is not made of things with definite properties in definite locations. It's made of quantum fields with probability amplitudes, and definite facts only crystallize when interactions occur. The whole universe is like an infinite double-slit experiment, with vast probability waves constantly interfering, constantly collapsing, leaving traces we call events, history, the experienced present. And Feynman's path integral showed us that the familiar laws of physics, the reliable ordinary rules we navigate by every day, are not bedrock. They are emergent, statistical, average behaviors. Under them lies a quantum reality, where every possibility is always in play, always being summed over, always cancelling and reinforcing, producing the solid-looking world we navigate while hiding the shimmering strangeness of its true nature. What I find beautiful about all of this, genuinely beautiful, not just abstractly interesting, is what it tells us about the relationship between knowing and not knowing. At every stage of the story of light, the breakthrough came from someone being willing to say, "I don't understand this. The comfortable picture doesn't fit. I am going to sit with the discomfort, follow the logic, and find out what the universe actually does, rather than defending what I already believe." Michelson and Morley didn't find the ether. They didn't then cook the data to make it appear. They reported the null result, even though it upended a century of consensus. That intellectual honesty was what gave Einstein the raw material to build special relativity. Einstein didn't say, "The speed of light must add up like everything else. Let me find where the experiment went wrong." He said, "What if it doesn't? And what follows from that?" That question, followed with complete rigor, changed physics forever. Feynman didn't say, "This quantum strangeness must be an illusion. Let me find the hidden classical reality underneath." He said, "This is what the experiments show. This is what the mathematics demands, and I will build the most precise and beautiful theory I can from those facts, and I will never pretend to understand more than I do." There is something deeply liberating in this. We tend to think of not knowing as a weakness, an embarrassing gap to be hidden or papered over. But in the history of physics, not knowing is where all the action happens. The most important words a physicist can say are, "I don't understand this," because that's the open door. That's where the universe gets a chance to tell you something new. Let me end with something concrete and close to home. There's a beam of sunlight somewhere near you right now, or there was, or there will be. That light left the sun 8 minutes ago, or, in the photon's frame of non-reference, never traveled at all, being emitted and absorbed in a single, timeless instant. Each photon in that beam is a self-sustaining oscillation of the electromagnetic field, a ripple in the fabric of reality requiring no medium to propagate. It traveled through the vacuum of space at the universe's fundamental speed limit, a limit so absolute that the universe adjusts the geometry of time and space itself to enforce it. That photon, on its way, mathematically explored every possible path it could have taken to distant galaxies and back, through the core of the Earth, via paths we couldn't trace with any instrument, and arrived at your eye as the sum of all those possibilities cancelling and reinforcing in the precise quantum mechanical way that Feynman worked out. When it hit your retina, it kicked an electron out of a photoreceptor molecule with an energy determined entirely by its frequency, and triggered the cascade of electrochemical signals your brain processes into the experience of light. And we understand almost all of this, in extraordinary detail, with equations that are correct to more decimal places than any other theory in history. And we don't entirely understand what any of it ultimately means, what the wave function really is. Whether the photon really takes all paths simultaneously in some physical sense, or whether that's just a convenient mathematical tool. What the nature of the measurement problem is at its foundations. And that honest, we don't know, hanging at the end of all the precision, is not a failure. It is the frontier. It is the place where the next Feynman is already staring at equations that don't quite fit, already asking questions that make everyone else uncomfortable, already refusing to pretend to understand more than the evidence allows. The light in your world is stranger and more beautiful than you have been given permission to know. And now, maybe, you have a glimpse of just how strange and beautiful that is. Thank you for walking this path today. If this kind of deep dive into the nature of reality is what you come here for, there is so much more ahead of us. The nature of time, the arrow of entropy, what it means for something to exist, the mystery of consciousness. Each one a thread that pulls you into the strangest and most beautiful corners of what we know and don't know. Until then, take a moment, the next time you turn on a light, to remember what you now know is happening, and what remains deliciously, wonderfully unknown. See you next time.